It's Mrs. Weethy, and we're going to start our lesson 2 on electron configuration, which are the rules for electron configuration. So get your materials ready. You will probably need a periodic table and your chill. Let's roll. Okay, so what is electron configuration? Electron configuration is the arrangement of electrons in the electron cloud. So we've already established that the electron cloud is no longer these rings around the nucleus, but these three-dimensional regions. And so how are we going to determine where the probable location of those electrons are? Well, first we have rules that are going to help us do that. The first rule is called Aufbau's principle. Aufbau's principle shows us the electrons will occupy the lowest energy orbital that is available. So when I say lowest energy orbital, I mean the S, the P, the D, the F, and whatever energy levels that they are in. So this is what we're going to do. We are going to develop a chart. So in your chill, I want you to make something like this where you have the 7 energy levels, and then we're going to write in the sublevels. Alright, so in the first energy level we have the 1s, and in the second energy level we have the 2s, and we also have the 2p. In the third energy level we have the 3s, the 3p, and the 3D. In the fourth energy level we have the 4s, the 4p, the 4D, and now we're going to add in the 4f. Now we only have 4 orbitals, 4 sublevels that is, and so we're just going to fill in the rest of the energy levels with the S, the P, the D, and the F. So go ahead and do that while I am doing this myself. And then we're going to draw arrows to show the order in which these electrons are going to occupy these orbitals. So I'm going to finish up here with the 7p, the 7d, and the 7f. Okay, so now what I want to do is I'm going to draw arrows, and these arrows are going to tell us the order in which these electrons are going to occupy these energy levels. Alright, so first, electrons are always going to enter the 1s orbital. So I'm going to draw an arrow. Okay, now, next we want to go into the next lowest energy orbital, which is the 2s. So I'm going to draw an arrow to show that. Now my next lowest energy orbital that is available is the 2p. And I'm going to keep drawing these arrows in diagonals so I can see the order that electrons are going to occupy these orbitals. So we're going to go 2s and then into the 2p and into the 3s. My next lowest energy orbital is the 3p. And so I'm going to draw my arrow in this direction. So I go from the 3p into the 4s. Now I'm going to come to the 3D, 4p, 4s, and then my next lowest energy orbital is the 4D. That's the next one that is open. So we go from the 4D, 5p into the 6s. Next lowest energy orbital is the 4f, 5D, 6p, 7s, and then we're going to go to the 5f, the 6D, and the 7p. Now, these 3 right here that kind of form a triangle, they don't exist. So we're not even going to cover those. So here's what's going to happen. Previously we said that the order of the sublevels go from the, let's see, let me get the laser on here, go from the 1s to the 2s, 2p, and it would make sense just to follow it in order. 3s, 3p, 3d, 4s, 4p, 4d, but that doesn't happen. As I drew for you in a previous video, you start having all this interference and this overlapping and things like that. And so what happens is now that's what's taking place, is we have overlapping of these energy orbitals. So if we start with the 1s and we just follow the order that these electrons go, we'll have 1s, and then we go to the tail to the next arrow and follow that arrow, so we have the 2s, and then after the 2s we complete that arrow. We're going to go to the tail of the next arrow. Electrons are going to go into the 2p, and following that arrow we're going to go into the 3s, which still makes sense. Then after the 3s, go to the tail of the next arrow. Electrons are going to go into the 3p. Now here's where that overlapping takes place. So now we have the 3p, and after the 3p we have the 4s. So this is really important. So here's what happens. You have this 3d orbital. D is a slightly higher in energy than this s, even though it's in different energy levels. And that 3d kind of pushes that 4s into a lower level and has a little bit higher energy. So you have that interfering, that overlapping of orbitals that takes place. So we have the 4s. Now we're going to come to the tail of the next arrow, and electrons are going to go into the 3d. After the 3d, follow the arrow. We're going into the 4p, and then we're going to end that arrow with the 4s. After the 5s. After the 5s, we go to the tail of the next arrow, which starts the 4d. And let's just finish that up. So we have the 4d, 5p, and 6s. So this is the actual order that electrons are going to occupy energy levels and those orbitals. That is what is called Aufbau's principle. Now, our next rule is called Hund's rule. Hund's rule states that each orbital of equal energy will be occupied by one electron first before a second electron can enter. So here's an example. First of all, what do I mean by orbitals of equal energy? Well, you have a 2p, and in the 2p, so that's second energy level, p sublevel. And how many orbitals do we have in the p sublevel? There are 3. So we draw those orbitals by using dashes. Now each of these dashes represents an orbital, and because they're all in the p sublevel, those are orbitals of equal energy. Let's say that we have 4 electrons. We want to, by the rule, you want to put 1 electron, and we're going to show electrons by arrows. We want to put 1 electron in each of those orbitals before we can add a second. So I have 1 electron in all 3. Then I'm going to go back to that first, and I'm going to put my 4th electron in that first one. Now, here's the significance to this, which is very important. You have these 2 unpaired electrons. Okay, these are unpaired. The significance to these unpaired electrons is that they are available to bond. Very important concept. They are available to bond. That is the chemical reactivity of that particular element. Now let's do it again, but let's say we don't follow Hund's rule. Instead, we're just going to put those electrons, 1, 2, 3, 4, right in order. How many electrons do you have available for bonding? Absolutely none. And so that is the difference between following Hund's rule and not following Hund's rule. One shows you the number of electrons that can bond, and the other one does not. So you can mistake an element for being chemically stable when in fact it is not. The last one is called Pauli's exclusion principle. Pauli's exclusion principle states that no 2 electrons can have the same 4 quantum numbers. So what does that mean? Well, let's take a look at this. The number 1 indicates the energy level. That's one of the quantum numbers, the energy level. S is the second quantum number, the sublevel. Third, we have the dash, and the dash indicates the orbital, which is the third quantum number. Now, the fourth quantum number are the electrons. So we have one electron that goes into the orbital, and remember, you have a spin quantum number which says you can have 2 electrons, but they have to be in opposite spins. So you have one electron, and then we have the second electron, and that second electron is going to be in an opposite spin. So no 2 electrons will ever have the same 4 quantum number. That is what Pauli's exclusion principle means. The last thing in this video is the octet rule. The octet rule states that all atoms, when interacting with other atoms during chemical reactions, which is really important, it has to happen during a chemical reaction, try to achieve a complete octet. So what is a complete octet? It's when we have 8 electrons, now in the S and P sublevels, in the highest main energy level. Why do we use the S and P sublevels? Well, if you recall, the S sublevel can have a maximum of 2 electrons. The P can have a maximum of 6 electrons. And when you add them together, you get your complete octet. When you have a complete octet, that indicates chemical stability. Okay? So, that's it for this video. Until the next video, bye for now.